Okay, so here we are for our final lecture for this semester in our little physics class here. We have just a very little bit to do at the end of chapter 7. And then I wanted to introduce just the concept of um, potential energy and conservation of energy from the next chapter very briefly. We've already actually had a look at both of those concepts, so it won't be entirely new, but I wanted you to know at least something about it. There won't be any elaborate stuff on the upcoming exam from chapter 8, but there might be, one or two sort of very simple potential energy related questions, on the test. So, and it's a fairly important concept. So I wanted you to see at least a little bit of it before we end the semester. We were working last time on power. Whoops, there it is, power, which is defined as the amount of work or energy delivered per unit of time. And the units would be whether it's joule or whether it's work per unit of time or energy per unit of time, either way, the units would be joules per second, which are better known as watts. The symbol for a watt is a capital W. It is a metric unit, so you can use prefixes with it like milliwatt or megawatt. And also, we can also use units of horsepower for power. And 1 horsepower is 746 watts. At least according to the US standard for horsepower. So relating some different things together, we saw that power is the amount of work done in a given period of time, but that also works out to the force vector in a dot product with the velocity vector. And that can actually be useful for some problems, like for instance, the problem we're doing right here. We have a car that's actually going up a hill. It's a 15% grade, and the car has a mass of 1,200 kilograms. And the car needs to go up the hill at a constant speed of 90 kilometers per hour. And you can assume that 25% of the power goes to overcoming fraction and wind resistance. And so the question is, how much power does the engine have to put out in order to do that? First, a couple of things. They don't really mention what 15% grade means. So in case you don't know, what that means is that you basically rise 15 units for every 100 units you go horizontally. So basically, if you go 100 feet horizontally, you will have risen 15 feet. Or in terms of meters, if you go 100 meters horizontally, you will be 15 meters higher than you were when you started. So that's what 15% grade means. It means you gain 15 meters for every 100 meters horizontally. Also, notice the units for the velocity, 90 kilometers per hour. We're going to need to change that to meters per second, but we can do that in a little while. Now, notice it said constant velocity, or actually, I guess it didn't say explicitly constant velocity, but it gave a speed and it didn't say anything about acceleration or deceleration. So under those circumstances, you can assume that it means constant velocity. And if the velocity is constant, that means there's no acceleration. And that means there's no well, if there's no acceleration, there's no net force. If there's no net force, there can't be any net work, and there's no change in the kinetic energy. So the kinetic energy is constant. Power from the engine is basically going to be what's needed to overcome gravity and friction and air resistance. It's set up here in the problem that 25% of the power goes to overcome friction and air resistance. And so that applies that 75% of it must go to overcoming gravity. Okay, so we can say the work due to gravity is the force vector in a dot product with the velocity vector. And force for gravity anyway is weight, or in other words, mass times gravity. So we can change F dot V to mg dot V. And uh, let's see, in mg is just mg. For a v, the v is going uphill though, remember. So what we want in this case is the x component of the velocity, and that's going to be v sine theta. Remember, this is the action here is happening on an incline, so the x component is given by the sine of the angle, not the cosine like it is on level ground. So v sine theta. Okay, that begs the question, what's theta? They didn't tell us. But we can figure that out because we have the x distance here. Well, it didn't actually tell us how far the car was going, but we know that if it's a 15% grade, then we can just set it up basically for every 100 meters horizontally, you go up 15 meters. And it wouldn't really matter if you chose those values as long as you get the same proportion. We could have put the horizontal distance as 200 meters as long as we put the vertical distance as 30 meters. Okay, so either way, the angle is going to work out the same. So we have the x value for this little right triangle. We have the y value, and it is a right triangle for the right triangle. And the angle is just going to be the angle whose tangent is y over x, or the angle whose tangent is 15 over 100, and that comes out to 8.53 degrees. That's your theta. Okay. Now, remember what they're asking for, though, is the total power that's given off by the car. Okay, so as we said right here, the power to overcome gravity is 75% of the total. So work or power due to gravity is 70.75, that is P total, and that is mg v sine theta. And so if you want to rearrange that to find P total, it's just mg v sine theta over 0.75. So mass is 1,200 kilograms, g, gravity, 9.8 meters per second squared. V, now we have to figure v in meters per second. That was 90 kilometers per hour times 1,000 meters per kilometer. That cancels the kilometers. Times 1 hour for 3,600 seconds. And that cancels the hours and gives us meters per second, which is 25 meters per second. So that goes there. And the sine of 8.53 divided by 0.75. When you work that out, you get 58,144 watts, or 58.1 kilowatts. Since it's a car, you might want to measure the power in horsepower. Although, as I've said, in Europe, they've largely started using kilowatts instead of horsepower. But anyway, for horsepower, it's just 58,144 watts times the fact that there's 1 horsepower for every 746 watts. That will cancel out watts and leave you with 77.9 horsepower. Okay. So that's how much horsepower is actually being used to keep that car moving up the hill at a constant rate of speed. Hopefully that's not the maximum output of the car's engine, but that's what's actually being used now. And that is actually the final example from chapter 7. And what I would just like to go on now and do is just a very brief introduction from chapter 8. We won't get very far into it, and I'm not even going to cover everything that's done in the first few pages, because there are just some certain main points that I would like everyone to know. Chapter 8 is about potential energy and conservation of energy. There are, well, first of all, potential energy can be defined as a type of energy that is potential. So, brilliant, right? Potential meaning that it's not actually being expressed at the moment, but it could be. So like your potential as a human being, maybe you're not expressing it at the moment, but you could at some point in the future. Potential energy is energy that's not doing work right now, but it could at some point in the future. And it has the ability to do that at some point in the future. And we'll get to conservation of energy in a little while. Okay, so first of all, essentially any type of energy that's not really that's not engaged in doing work right now is potential energy. There are actually several different types of potential energy. And there's one that we'll be concerned about here, and then there are a bunch of others. Okay, so types of potential energy. There's essentially a type of potential energy for every type of interaction. And the total potential energy for any system would just be the total of all of the different types of potential energy in the system. Some of the types, and actually this is not an exhaustive list, but some of them that come to mind would be chemical potential energy. Since chemistry is my field, that's the first one I'd think of. There is a certain amount of energy that's stored up in the bonds within molecules. And if you want to break up a molecule into into its constituent atoms, you have to put energy in to do that. You have to overcome the energy that's stored in those bonds. And on the other hand, when you form new bonds, the molecule releases energy. And since a chemical reaction essentially consists of taking some molecules and breaking their bonds and rearranging the atoms and forming new bonds, that means that chemical reactions can take in or give off energy overall. Like, for instance, burning gasoline. That's a chemical reaction where you're burning gasoline in the presence of oxygen. The carbon in the gasoline becomes carbon dioxide. The hydrogen in the gasoline becomes water vapor. And that's accompanied by a giant release of energy. And that's because you only have to put a little bit of energy in to break the bonds in the gasoline and the oxygen from the air. But then when you form the new products, there's a whole lot of energy released from the new bonds. And so, and the energy, when it's in those bonds, is considered potential energy. There's electrical energy. Electrostatic energy would probably be a better name for this, because this is the energy that you have when you have two charged particles that are being held a certain distance apart from each other. Whether they attract or repel each other, either way, there's a certain amount of energy that's stored up in that condition. And it's sort of like holding magnets a certain distance apart. When you have two magnets that are attracted to each other like these two are, and you have to hold them a certain distance apart, you can tell it takes a certain amount of effort to hold them apart from each other and not let them touch. And so there's a certain amount of potential energy that's stored up in that situation. Even if you turn them around so that they repel each other, again, it takes a certain amount of energy to hold them together close to each other and not let them just fly apart. And so that, again, is another form of potential energy. Magnetic or electromagnetic potential energy. There's elastic potential energy. That's kind of potential energy you would have in a coiled up spring. It can do work at some point in the future, but it's not doing any right now. And there's gravitational potential energy. That's the one that we're going to be most concerned about here. Gravitational potential energy is a potential energy that something has because of its position within a gravitational field. And that's just fancy talk for what we usually mean by position within a gravitational field is its height above the ground. Whenever an object is near planet Earth or any other heavenly body, the gravity of that heavenly body will be trying to pull the object in toward the center of the Earth or that heavenly body, whatever it is. And the fact that the object is being held a certain distance above the center of mass of the Earth means that there's a certain amount of potential energy stored up in that object's position, which could be expressed in the form of, say, kinetic energy if you were to drop the object or if it were to fall. And so that's why it's called potential energy, because it's basically stored up. On planet Earth, which is where we normally deal with things, gravity near the surface is going to be 9.8 meters per second squared. Or in other words, what that means is that the attraction of gravity causes things to accelerate toward the Earth at a rate of 9.8 meters per second squared. Technically, gravity is pulling from the center of the Earth, but you can't really get there without hitting something else first. And so we normally measure things relative to, say, ground level. Actually, the 0 point in terms of kinetic energy, or in terms of potential energy, can be kind of arbitrary. And you usually assign the 0 point as being the lowest point, that is, the lowest point in elevation that's relevant to the problem. So in a lot of cases, it might be ground level, but in other cases, it might be sea level, or it might be the base of a mountain, or the first floor of a building, or maybe the floor, if something is falling off a shelf, the floor might be considered the 0 level, or something like that. But, technically, to be perfectly rigorous about it, the 0 point should be the center of the Earth. When we take changes in potential energy, first of all, the symbol for potential energy is, in physics, U. And delta U just means change in potential energy. So the change in potential energy due to gravity would be the negative of the work that would have to be done against gravity to hold the object where it is. And so, when I hold when I hold a bunch of keys up above the table, it takes a certain amount of work to do that. And the work that I'm doing is a work against gravity. And if I were to drop them, they will fall until they hit something like the table. And that means that when the keys are up here, they have a certain potential energy because they have a certain height above the ground. And when I drop them, they have a certain lower potential energy because their height above the ground is lower than it was before. And so the change in potential energy is the negative of the work that you would have to do above potential against gravity in order to raise the object to the same height. So in other words, the change in potential energy of these keys between here and here is the negative of the work I would have to do to raise them up from that height. And that is equal to mass times gravity times the change in the vertical position. The change in the vertical position is usually spoken of as height. So you could also think of this as mg delta h, as mass times gravity times the change in height. And we actually had, I think it was 2 problems in the last chapter where we used this formula. So we were actually dealing in potential energy, only they weren't telling us, although I did mention it during the lecture. I remember the problem where we took a library book down off the shelf and then carried it horizontally. Well, when you're taking it down off the shelf, the change in energy of the book that we calculated was according to this formula here, mg yb minus ya. That is mg delta h, in other words. So that was the change in kinetic energy. If an object is just sitting still, its kinetic energy is given by mgy, in other words, its position in the y direction, which is just another way of saying mgh plus some constant. So in other words, potential energy is mgh, or mass times gravity times height. Okay, that's an example. Let's see, go back to number 2. So again, in terms that might be a little more understandable, gravitational potential energy, or U, or sometimes referred to as PE, is mgh. The units I haven't mentioned yet would be mass times gravity times height. SI units for mass would be kilograms. SI units for gravity would be meters per second squared. And SI unit for height would be meters. So when you put those together, you get kilograms meters squared per second squared, and that's a joule. So potential energy can be measured in joules also, just like kinetic energy. And again, if the height is changing, the change in potential energy is just mass times gravity times the change in height. Okay, so same thing again. And that brings us to conservation of energy. Conservation of energy means or refers to the fact that the total amount of energy in the universe is constant. Or in other words, the total amount of energy in the universe doesn't change. Energy cannot be created or destroyed. It's all out there somewhere already. But what you can do is you can transfer it from one place to another, or you can change it in form. Potential energy can become kinetic energy, which can be changed back into potential energy. Or chemical energy can be changed into kinetic energy, like when you burn gasoline in your car. You're releasing the potential chemical energy in the gasoline and the oxygen from the air, and you're turning it into kinetic energy that makes the car go down the street. Theoretically, though, well, actually, in actuality, too, the amount of energy that you're releasing from the molecules in the gasoline and the oxygen when you burn them in the engine is equal to the total energy that's released. So because of all the different places it can go, though, some of that energy is released in the form of heat, some of it's released, some of it's used to overcome friction, and some of it is used as kinetic energy to move the car. So when you total up all of those different basically all of those different things that the chemical energy turns into, it turns out that energy is conserved. The chemical energy from the gasoline and the oxygen is equal to the total of all of those other forms of energy that are given off, like the heat and the work against friction and the kinetic energy. They should be equal. Okay, so it can change its type. And a good example of changing from one form of kinetic energy to another and conservation of energy is that, say, for example, if you have a book that's on a high shelf and it falls off onto the floor. When the book was on the high shelf, it had high potential energy. And now that it's fallen on the floor, it has much lower potential energy because it's less high above the ground. And as it turns out, the kinetic energy that the book had while it was falling is exactly equal to the difference between the potential energy when it was up on the shelf and the potential energy now that it's on the ground. Or in other words, the potential energy on the shelf is equal to the potential energy on the floor plus the kinetic energy in going from the shelf to the floor. And this is basically what we mean by conservation of energy. The energy can't just disappear, and it can't just disappear or appear out of nowhere. It has to go somewhere. And in this case, the potential energy when the book was up on the shelf went here and here. And if you could calculate those two things, you could figure out, or you could prove that energy is indeed conserved. Some of the energy might go to overcoming wind resistance, although in this case probably wouldn't be very much. But if you account for all of the different places that the energy is expended, you would find that energy really is conserved. And let's see, another example of that relationship between different types of energy and also conservation of energy comes in projectile motion. When you launch a projectile into the air, you have to do work on the projectile to get it to launch into the air. And when it first takes off, the kinetic energy should be the same as the amount of work done on the object to get it into the air. And that will be the maximum kinetic energy that the object has. Also the minimum potential energy because it's on the ground, well, assuming it's on the ground. As the object rises up, it's slowing down as it goes higher and higher. And so its kinetic energy is decreasing while its potential energy is increasing because it's higher above the ground. When it reaches the apex of its trajectory, that's the point where it has maximum potential energy because that's the highest it ever gets above the ground. And that's also its minimum kinetic energy because that's the slowest point. And in fact, it stopped moving in the y direction, although it still is moving in the x direction. So that's the minimum kinetic energy. As it comes back down, it starts speeding up again. So the kinetic energy increases while the potential energy decreases because it's getting closer and closer to the ground again. And then when it lands, it should have, again, the maximum kinetic energy, the same as it had when it was launched, and also the minimum potential energy, assuming that it lands at the same level it took off from. Okay. And it should also be the case, theoretically anyway, that the total of the kinetic energy and potential energy of that projectile should be the same at any point along the trajectory, because they sort of rise and fall in inverse proportion to each other. So it doesn't matter where along here, the total of KE and PE should always be the same. Okay, and some of this is basically stuff we've done before. As I said, the 0 point in terms of gravitational potential energy can be designated within a given problem, depending on whatever point is most convenient, because it's all relative. So usually the 0 point is taken as the lowest elevation within a given problem. In many cases, that would end up being the ground, but it wouldn't necessarily have to be. Okay, and an example of that is actually the second example in the chapter. That's the only example I want to go over. The first example isn't really relevant to what I want you to know, but this one is. You have the summit of some hill in Massachusetts is 147 meters above its base and 195 meters above sea level, or in other words, the base is 48 meters above sea level. And a 75 kilogram hiker is climbing from the base to the summit. What is the gravitational potential energy of the hiker Earth system? What that really, that's a fancy way of saying, what is the gravitational potential energy of the hiker relative to the Earth with respect to the base? In other words, what they mean with respect to the base, what that means is the base of the mountain is the 0 point for potential energy. When the hiker is at, say, the base of the hill, well, okay, this is a little repetitive. If the base is the 0 point for kinetic or potential energy, then the potential energy of the hiker at the base is going to be 0, right? And it is, because if we're taking the base as the 0 point for potential energy, that implies that the base is 0 height, relatively speaking, at least for this problem. And well, that would mean that the potential energy of the hiker at the base is mgh. So 75 times 9.8 times 0. And that's 0. Okay, at the summit is 147 meters above the base. And so your height here is 147 meters. So the potential energy at the summit is, again, mgh, 75 times 9.8 times 147. And that is 108,045 joules, or you could report that, because this is kind of a ridiculous number of significant figures anyway, you could count that as 108 kilojoules. And what we know now, that is the potential energy of the hiker at the summit. The potential energy of the hiker at the base was 0. And so the change in potential energy from the base to the summit is 108 kilojoules. What that also tells us is the kinetic energy that the hiker expended in getting from the base to the summit is 108 kilojoules. It's kind of the reverse of the book falling off the shelf. And again, that's because of conservation of energy. Now, at sea level, if the base of the hill is 48 meters above sea level, that would mean sea level must be 48 meters below the base. Or in other words, 48 meters below 0 in terms of our height scale. And so your height at sea level is minus 48. So the potential energy at sea level relative to where we set the 0 point for this problem would be mgh, that's 75 times 9.8 times negative 48. And that's negative 35,280 joules, or negative 35.3 kilojoules. Okay, so you can have negative potential energy. You can have negative height relative to some other point. And so, yeah, it is possible to have negative potential energy. It all really depends on where you set the 0 point. If you set the 0 point as being the ground, then you can have negative potential energy if you go below the ground. If you set the 0 point at the center of the earth, which theoretically is where it should be, then in that case, you really wouldn't be able to have a negative potential energy. But because the center of the earth is not really convenient, you'd have to be able to measure basically the distance from the ground to the center of the earth at any given point in order to know, if you wanted to use the center of the earth as a 0 point, that would get really complicated. So people usually just use the ground or some other convenient point to be the relative 0 point for potential energy calculations. If it's hiking a mountain, then the base of the mountain might be the 0 point. If it's a book falling off a shelf, then the floor might be the 0 point. Even if it's the 10th floor of a building, that would still be a good 0 point. Okay. Well, that's sort of a quick introduction to potential energy. And so you should be able to do simple problems like the one that we just did for the exam. And that will be posted either tomorrow or Wednesday. And like I said, I will send out an email once it is posted. And so be on the lookout. Okay, well, good luck and happy holidays.